Welcome back. In this video, we are going to explore Chapter 3, Single Variable Linear Inequalities. Throughout this chapter, we will cover 4 essential sections. First, Section 3.1 introduces the core concept of inequalities. Next, Section 3.2 explores the practical applications of inequalities. After that, Section 3.3 focuses on solving compound inequalities. Finally, Section 3.4 guides us through absolute value inequalities. Let's dive into Chapter 3 together and master these core concepts. An inequality is a mathematical sentence that states that two expressions are not equal. We use 4 core symbols to represent these relationships: the less than symbol, the greater than symbol, the less than or equal to symbol, and the greater than or equal to symbol. For example, we read the expression y is greater than or equal to 5 to show that y can be 5 or any number bigger than 5. Now let's show an inequality on the number line. Our problem is to graph x is greater than 3. This represents the interval where numbers are strictly greater than 3. To draw this, we place an open circle at the endpoint 3. The circle is open because 3 is excluded from the solution. Then we draw a bold arrow pointing to the right. In interval notation, this open interval is written as 3 to infinity. The addition property of inequalities states that if we add the same number to both sides of an inequality, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b, then a plus c is greater than b plus c. Let's apply this to example 1. Solve and graph the solution of x minus 4 is greater than 2 on a number line, and write the solution in interval notation. To solve, we start with x minus 4 is greater than 2. Using the addition property, we add 4 to both sides. This simplifies beautifully to x is greater than 6. Now let's look at the graph. We place an open circle at 6 because 6 is not included, and draw a bold arrow to the right. Finally, the solution in interval notation is written as open interval 6 to infinity. The subtraction property of inequalities states that if we subtract the same number from both sides of an inequality, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b, then a minus c is greater than b minus c. Let's solve example 2. Solve and graph the solution of 4x is less than or equal to 8 plus 3x on a number line. Write the solution in interval notation and state the maximum integer value of x that satisfies this relationship. To solve, we subtract 3x from both sides. This simplifies directly to x is less than or equal to 8. For the graph, we place a solid closed circle at 8 because 8 is included in our solution, and draw a bold arrow pointing to the left. In interval notation, this is negative infinity to 8 with a bracket. Therefore, the maximum integer value of x is exactly 8. The multiplication property of inequalities states that if we multiply both sides of an inequality by a positive number, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b and c is greater than 0, then a times c is greater than b times c. Notice that the direction of the inequality stays the same. Let's look at example 1. Solve the inequality 1/3 of x is greater than 4 and graph the solution on a number line. To clear the fraction and isolate x, we use the multiplication property. We multiply both sides of the inequality by positive 3. Since 3 is positive, the inequality sign remains the same. This simplifies perfectly to x is greater than 12. On the number line, we place an open circle at 12 because 12 is excluded and draw a bold arrow to the right. The final solution in interval notation is written as open interval 12 to infinity. The division property of inequalities states that if we divide both sides of an inequality by a positive number, it gives an equivalent inequality. Given real numbers a, b, and c, if a is greater than b and c is greater than 0, then a over c is greater than b over c. Just like multiplication, dividing by a positive number keeps the inequality sign in the same direction. Now let's tackle example 2. Solve the inequality for x is greater than 15 and graph the solution on a number line. To isolate x, we apply the division property and divide both sides by positive 4. Since 4 is a positive number, the direction of the inequality remains exactly the same. This simplifies to x is greater than 15 fourths. 15 fourths is equal to 3.75. On the number line, we place an open circle at 15 fourths because this point is excluded and draw a bold arrow pointing to the right. The solution in interval notation is written as open interval 15 fourths to infinity. This is really important, so make sure you listen carefully. When we multiply both sides of an inequality by a negative number, the relationship reverses. Given real numbers a, b, and c, if a is greater than b and c is less than 0, then a times c is less than b times c. Remember, you must reverse the inequality symbol, otherwise the statement will be false. Let's solve example 3. Solve the inequality negative 1/3 of x is greater than 3 and graph the solution on a number line. To isolate x, we need to clear the fraction by multiplying both sides by negative 3. Because we are multiplying by a negative number, we must reverse the inequality symbol. The greater than sign flips to a less than sign. This simplifies beautifully to x is less than negative 9. On the number line, we place an open circle at negative 9 because negative 9 is excluded and draw a bold arrow pointing to the left. The final solution in interval notation is written as negative infinity to negative 9. Just like multiplication, the division property with negative numbers is crucial. If you divide both sides of an inequality by a negative number, you have to reverse the inequality symbol, otherwise the statement will be false. Given real numbers a, b, and c, if a is greater than b and c is less than 0, then a over c becomes less than b over c. Now let's look at example 4. Solve the inequality negative 7x is less than or equal to 28 and graph the solution. To isolate x, we divide both sides by negative 7. Since we are dividing by a negative number, we must reverse the inequality symbol. The less than or equal to sign flips to a greater than or equal to sign. This simplifies beautifully to x is greater than or equal to negative 4. On the number line, we place a solid closed circle at negative 4 because it is included and draw a bold arrow pointing to the right. The final solution in interval notation is written as bracket negative 4 to infinity. To solve multi-step inequalities, we combine several techniques. Our main goal is to isolate the terms with x on one side and isolate the numbers on the other. It is often easiest to keep the x terms on the side where they will have a positive value, so we can avoid dealing with negative coefficients later. Let's look at example 1. Solve the inequality. 5x minus 9 is greater than 2x, and graph the solution on a number line. First, let's eliminate negative 9 from the left side by adding 9 to both sides. This gives 5x is greater than 2x plus 9. Next, we move the 2x term to the left side by subtracting 2x from both sides. This simplifies beautifully to 3x is greater than 9. Finally, divide both sides by 3 to isolate x. The solution is x is greater than 3. On the number line, we place an open circle at 3 and draw a bold arrow to the right. In interval notation, this open interval is written as 3 to infinity. When tackling more complicated inequality questions, we can break them down into easier steps using a useful checklist. First, multiply out any parentheses. Second, simplify each side of the inequality. Third, remove number terms from one side. Fourth, remove x terms from the other side. And finally, multiply or divide to get an x coefficient of 1. Let's apply this checklist to example 2. Solve the inequality. 5 times x minus 2 minus 2 times x minus 5 is greater than 2 times x minus 4. Step 1. Multiply out the parentheses using the distributive property. This gives 5x minus 10 minus 2x plus 10 is greater than 2x minus 8. Step 2. Simplify the left side by combining like terms. Negative 10 and positive 10 cancel out, and 5x minus 2x leaves us with 3x. So, 3x is greater than 2x minus 8. Step 3. Remove the 2x term from the right side by subtracting 2x from both sides. This simplifies neatly to x is greater than negative 8. Our coefficient is already 1. On the number line, we place an open circle at negative 8 and draw a bold arrow to the right. The interval notation is written as open interval negative 8 to infinity. Today we are going to learn about solving conjunctions. The solution to a conjunction must satisfy both inequalities. This means that both individual inequalities must be true at the same time. Let's solve example 1. Solve and graph the inequality. Negative 5 is less than 3x plus 1, which is less than 7. Our main aim is to isolate x all by itself in the middle. First, let's subtract 1 from all three parts of the inequality. This gives negative 6 is less than 3x, which is less than 6. Next, to get x completely by itself, we divide all parts by positive 3. This simplifies beautifully to negative 2 is less than x, which is less than 2. So, our solution is any number greater than negative 2, but less than positive 2. Let's look at the graph. We place open circles at both endpoints, negative 2 and 2, and draw a bold red line connecting them in the middle. Now let's talk about solving disjunctions. Disjunction problems always include the word or. The solution to a disjunction is all the numbers that satisfy either one inequality or the other. Let's look at example 2. Solve and graph the solution set of 2x minus 5 is less than negative 3, or 2x minus 5 is greater than 3. To solve, we handle both inequalities. First, let's add 5 to both sides of both inequalities. On the left, it simplifies to 2x is less than 2. On the right, it becomes 2x is greater than 8. Next, we divide both sides of both inequalities by positive 2. This gives x is less than 1 or x is greater than 4. This means our solution includes any number smaller than 1 or any number larger than 4. Let's check the graph. We place open circles at 1 and 4. From 1, we draw a bold arrow to the left, and from 4, we draw a bold arrow to the right. Absolute value inequalities are just another form of compound inequalities. An absolute value inequality can have a form such as the absolute value of x is less than m. This means that x is restricted to points on the number line less than m units from 0, in either the positive or the negative direction. Therefore, the absolute value of x is less than m is completely equivalent to negative m is less than x, which is less than positive m. Let's look at a clear example to understand this perfectly. Suppose we want to solve and graph the absolute value of x is less than 4. Based on the definition, this means x represents all numbers whose distance from 0 is strictly less than 4 units. So, we can rewrite this absolute value inequality into a sandwich compound inequality. Negative 4 is less than x, which is less than 4. Let's look at the graph. We place open circles at both endpoints, negative 4 and positive 4, because the distance is strictly less than 4. Then, we draw a bold red line connecting them in the middle. In interval notation, the solution set is written as the open interval from negative 4 to 4. Today we will learn how absolute value inequalities can be written as conjunctions. An inequality of the form absolute value of mx plus c is less than v can be rewritten as the compound inequality negative v is less than mx plus c, which is less than v. Let's solve example 1. Solve the inequality absolute value of x minus 3 is less than 5. First, we rewrite this absolute value inequality as a conjunction. This gives negative 5 is less than x minus 3, which is less than 5. Next, to isolate x by itself in the middle, we add 3 to all 3 parts. This simplifies beautifully to negative 2 is less than x, which is less than 8. So, our solution interval is open interval negative 2 to 8. On the number line, we place open circles at negative 2 and 8, and bold the segment between them. Next, let's talk about converting absolute values into normal disjunctions. An absolute value inequality of the form absolute value of mx plus c is greater than v is the same as the disjunction mx plus c is less than negative v, or mx plus c is greater than v. Let's look at example 3. Solve the compound inequality absolute value of 2x minus 1 is greater than 5. First, we write the inequality as a disjunction. This gives 2x minus 1 is less than negative 5, or 2x minus 1 is greater than 5. To get x by itself, we add 1 to all parts, getting 2x is less than negative 4, or 2x is greater than 6. Then, dividing by 2, we get x is less than negative 2, or x is greater than 3. Our solution set in interval notation is the union of open interval negative infinity to negative 2 and open interval 3 to infinity. On the graph, we place open circles at negative 2 and 3 and draw arrows pointing outwards to both. sides.